Okay, so I just want to talk a little bit about the hydraulic system that's in a braking system. And I'll talk a little bit about the basics of hydraulics, and then we'll talk about the service and what actually gets done with hydraulics in a braking system. So, we have a few laws here. So we have Pascal's Law, which tells us that fluids are, pressure inside fluids is transmitted equally and undiminished in all directions. So equally and undiminished in all directions. So what does that mean? So I've got a very simple system here. I've got an input piston where I'm putting 10 pounds of force in, and I've got an output piston where some amount of force is going to come out. All right, so if we take and put 10 pounds of force on that input piston, force is transmitted equally and undiminished in all directions. That means then that 10 pounds of force is getting pushed everywhere, okay? And what 10 pounds where? How much? Okay, well it's 10 pounds of force per a surface area, right? So if we look at this input piston, right, let's make it easy. Let's say that this is 1 inch square. Let's say that that's the surface area of this round piston. So we would have 10 pounds of force per 1 inch squared. So that means that every 1 inch square of surface area, there'd be 10 pounds here, 10 pounds here, 10 here, 10 here. Okay, so all this system everywhere gets 10 pounds of force for every 1 inch square. Now if this is solid steel and it can't go anywhere, and this is a steel braided line and it can't move anywhere, and this is steel and it can't go anywhere, then this hydraulic pressure and force really does nothing pushing against there. But here, if it pushes against this piston, we get 10 pounds of force here, 10 here, 10 here, and we're pushing this with a much greater force than what we put in. So if you can imagine that this is a bigger piston like so, right, we might get 1, 2, 3, 4, 5, I don't know, say 10 of these circles, 1 inch square circles in here. Right? So that means that we're getting 10, 10, 10, 10. We're getting 100 pounds of force if this is 10 inches square. So we're increasing that force. Now we are losing something. So if you can imagine that this piston moves this way and we take all this fluid here and we have to put it in this big space here, we might only get this much movement, and we call that stroke. So the length of travel of this output piston would be decreased, or what we call a decrease in stroke. So we can use hydraulics both ways. There may be a situation where we have an excess of pressure, like a hydraulic pump in a tractor or something, and we want to have a long stroke, like a gravel fork on a bucket, right? So we don't need a whole bunch of force to lift a gravel fork, so we have a smaller cylinder, and then we have a long cylinder that can have a long stroke. And we're using that oil to take and move that thing a long ways, right? If we used a big cylinder, that would take a ton of oil, but have a lot of force. So it's all just a big balance, okay? So if we look at a braking system, let's see where and how that all starts. So in our braking system, we start with mechanical force. So we have a mechanical force that's pushing on this input piston. Where does that come from? That comes from me, the driver. You, the driver, comes from your foot, your energy. So you physically take and push on that pedal, and you're moving that pedal and pushing force on that hydraulic piston. Now, you're getting a force increase because your pedal is really, really long. Okay? If this was the pedal, okay, and it's attached way up here, you've got a big, long fulcrum. You got a fulcrum up here with a big long lever that you can take and increase force in. Okay, so you're getting an increase of force there. And you're pushing on a piston. So inside this master cylinder, okay, so it looks something like this, you have a piston that looks something like this. Okay? And so we'll have a piston here. This isn't the right one, it's a little small for this master cylinder. But this piston would be in here like this, and it's actually two separate pistons. So we have a hydraulic area here and a hydraulic area here that get pushed on with one rod. So you're pushing in here, you're moving this piston, and you're taking that mechanical energy and you're converting it to hydraulic flow, just like inside here. But we're doing it with two separate systems. So we have one system coming here, one system coming here. So we'll have one hydraulic pressure system feeding two brakes. Now it may be two front brakes, okay? It may be a front brake and a back brake diagonally split. Depends on the weight of the vehicle and how weight's transferred with the vehicle. We'll get into that in just a second as well. Then the other system will feed the other two, maybe two back brakes or the other two horizontally opposed ones, or diagonally opposed ones, if it's a diagonally split system. So why do they do that? Well, if we had one system, it would work. Okay? We know that fluids are transmitted equally and undiminished in all directions. We could hook up 10,000 lines here and we would have the same pressure on every single one. Now that would be a lot of oil, right? And we wouldn't have the fluid to fill 10,000 lines, but 4 we could do, right? There's not a whole lot of movement in these brakes, right? They only move a little bit. So we could do 4 with one piston. But if it broke and this hydraulic fluid got out, we would lose all the pressure, right? Fluid's going to take the path of least resistance and it's going to come out here instead of squeezing and making those brakes work. So if we lose a brake line, we don't want to lose all our brakes. If we split it up into two systems and this brake hose failed or this brake line breaks, then we only lose 2 brakes, not all 4. So that's why they do it. It's 100% for safety. It's called a dual braking system. Now, I talked a little bit about how sometimes it's the front brakes and back brakes, sometimes it's diagonally split. The decision to do that has nothing to do with the back being drum or front being disc or 4-wheel disc or anything like that. The decision to do that depends on how the weight transfer is of the vehicle. So if it's a front wheel drive vehicle and the front tires are doing the driving and there's a lot of weight up in the front and you brake and that vehicle shifts forward quite a bit, the front tires are doing about 80% of the braking. So if we split that and had a front system and a back system and the front system went, we would only be left with 20% braking. So in that situation, we would diagonally split them so you at least get 40% and 10% and you're left with 50% of your braking. Okay? Why is it diagonally split and not side to side split? Well, if we lost one whole side and one side of the vehicle was able to brake, that side would stop turning, this side would drive, and it would pull that vehicle over potentially into traffic and things like that. That's how bobcats steer, right? We can stop or turn one tire backwards, the other one forwards, and we can spin on a dime. Okay? So that's why it would be diagonally split. Trucks or something where there's more weight in the back and a longer wheelbase, the back would do about 40% of the braking, front would do 60, so they might do a front-back split because 40 is sufficient enough to at least get you to stop braking. Okay? So that's sort of the basics of how hydraulics work to increase force. So just to review it, we have mechanical force here, converting it to mechanical energy. So we have a small piston inside here. So let's say we get 10 pounds of force on here. That's 10 pounds per roughly 1 square inch. We'd have to measure it, but let's say it's 1 square inch. So now we get that 10 pounds of force on every 1 square inch here. So if we look at the back of the caliper, right? Okay. If we look at the back of the caliper here, there would be 2 pistons. I don't know if can you see that? All right, so there'd be 2 pistons here that are roughly that big, right? So we get that force increase. If you can imagine, right, we could fit 1, 2, 3, maybe 4 in each of those. So we're getting 8 times the force increase with this hydraulic system. And that force increase squeezes on that with a ton of more force, so we can really squeeze that tight and stop that. Okay? If we don't have enough squeezing pressure, we can't stop this as easily. Okay? Now, one thing that we're missing is when you look at a master cylinder on a vehicle, there's usually that big kind of drum back in there. It looks like a big pot. You may be wondering, like, what is that? So that is a vacuum brake booster or power brake booster, and it uses your engine vacuum to assist in your pushing. So you might push 10 pounds with your foot, you get the mechanical increase of the lever, so maybe you're pushing 50, you get the power brake booster pulling on it, so you might, maybe put 100 pounds of force in here, right? And then if you're timesing it by 8, right, you're getting 800 pounds of clamping force in there. The drum brake, roughly the same size. right? So we're not getting a whole lot of force increase, but if you remember, the drum brake self-energizes. You just got to get it started, and it wedges itself in there, and you're really just making sure that there's enough hydraulic pressure so they can't close, and it just lets it wedge in there as it brakes. Okay, the more you push it out, the more it wedges in there, and so it's self-energizing. And then if we take that pressure away, the spring pulls it closed. Okay, so that's basically how the hydraulics work. So what do we need to look for? Okay, well, in a hydraulic system, we need to assess the fluid. So the fluid in here, we call it fluid because it's glycol based. It's similar to coolant. It's not an oil, okay? So it's glycol based. It will has a very, very low freezing point, very, very high boiling point, and an extremely consistent viscosity in between. It doesn't get thick, and it stays at that proper viscosity for a wide range, just like the coolant in your car. It doesn't get thick at -40, and it looks the same at +40. So it's a glycol-based fluid. The other reason that it's glycol-based is it can mix with water. Now we don't mix it with water. There's no water in here, but if water got in here and permeated through the seal or the casting porosity, and somehow we got this little pocket of water in here, if this was oil, it would be a pocket and it would be separate because oil and water don't mix. And then we would get this pocket of water in here that would potentially freeze or would freeze, right? And if we have a big frozen chunk of ice inside here and I press the brakes, fluid can't get past it and those brakes don't work. But if I have a fluid in here that can absorb water, then that water just becomes part of it, right? It would raise the freezing point slightly, but at least it's not going to freeze the whole thing. So in a brake service job, it's very important to check that fluid. So you can check it for color. It starts to, when it deteriorates, it starts to get a little dirty looking. But also there's test strips that we use as technicians. We can test it and look at the test strip and see the percentage of water. And there's certain allowable amounts, and as it gets up high enough, it's time to flush and clean and take all that fluid out. So assessing your fluid is an important part of your brake system. One common thing that a lot of people sometimes do is when we put new pads on, we have to take and push that piston all the way back in. But if we leave all this brake fluid right here and we just push it back into the reservoir, we're potentially pushing all this damaged fluid back in here. Because the fluid that's right next to the rotor is exposed to the highest heat. So the most deterioration of the fluid happens in here, and we don't want to just take and shove it back in there. So often what technicians will do is crack the bleed screw when they push this in and let that fluid come out, and then close it, and then replenish with new fluid, okay? Or do a full flush. Right? So that's an important part of the system. Other important parts is simply inspection. So making sure that none of these lines are the steel ones, hoses are the rubber ones, making sure that none of those are damaged. So the hoses, checking for cracks and things like that. It's a rubber hose with steel braiding on the outside and then another rubber hose over it. So if this external hose cracks, moisture gets in there, deteriorates and rusts the metal, and now that hose can't handle the pressure. So it'll be fine for braking until that emergency situation. You have to brake really, really, really hard, and that thing pops and blows on you. So making that assessment of all those hoses and checking and making sure that there's no leaks. Okay? So that's the majority of the things that we do with the hydraulic system. Then if we open the system at all, so if we did change a line or anything like that, then we have to take and bleed the system. And so what's happening there is if we get a pocket of air in here, okay, and that air sits in here like this, unlike fluids, air is compressible. So fluids are incompressible. That's what makes them transmit force equally and undiminished in all directions. But air is compressible. So if I press on this piston and I transmit this force equally and undiminished, it's going to exert its pressure on this gas, this air, and it's going to squeeze that bubble and make it come smaller, instead of transmitting its full force to this piston to push it out. So if we have air in the system and we press on our pedal, we're just squishing air. You get that spongy feel to your pedal. So we want to bleed that air of the system. But this isn't something you normally have to do with a brake job if you're just changing friction components, because that system hasn't been opened. But if the system has been opened, we typically need to, or we have to, bleed the brakes and get all that air out. Okay, so that's another whole process and a different lesson, but that's something that technicians would do, is bleed that system and get it out. In short, basically we open this screw up while we push on the brakes, and we squirt fluid here, and we get little bubbles of air, and then we close it quick so that when we release this, we don't suck air back in, and we just repeat that process. So yeah, so that's how we would bleed brakes. And you would do the same thing to do a brake fluid flush. You could crack this and suck all the fluid out with a vacuum bleeder, or just simply keep bleeding brakes until you get new fluid coming out of each line. Okay. Now, another thing that technicians do is if you're changing something like this, or if this line blows on you and this gets empty, you can get air in this whole system, in your ABS controller, and it can be really difficult to bleed. So it's very important not to open up these systems unless you know what you're doing, if you're a trained technician. So if you are doing that, right, typically what technicians will do is, do it quickly, or make sure you have a pot up here with extra fluid, or, put your fingers on here and hold it, and then get the new one on, so that your last thing you're changing is the last thing that's going to lose fluid, and you don't lose too much, and you can, keep fluid in the system, so it's easier to bleed. So there's some tricks to doing that. It's quite a difficult thing to do at times. If you do get air in your ABS system, you need to hook up a scan tool, cycle solenoids, and things like that to be able to bleed it properly. Okay, so that's basically the hydraulic system, right? We have the master cylinder, wheel cylinder, caliper, all the lines in between, the ABS controller, and things like that aren't in this demo, but we just need to inspect all of those things. Okay, I think that's it.